Here's an introduction to cosmology to accompany chapter 29 of the textbook Astronomy from Open Stax. So cosmology, what is cosmology? You may not have heard the term before. It basically just means the study of the structure of the universe over time. So how do we go from the very beginning, when everything was a compact point, to the universe now that has our galaxies and stars inside the galaxies, and the galaxies are in clusters and is rapidly expanding apart. So describing this whole sort of large-scale evolution is the goal of cosmology. And this starts about 14 billion years ago. That's from the Big Bang. You can think about, okay, well, what's before that? It really becomes a bit more philosophy than anything else. So about 14 billion years ago or so, everything was compacted into an infinitesimally small point, and that began rapidly expanding. And that whole thing is our universe. And you might say, what's it expanding into? That's not the right way to think about it. Everything's expanding. So it's a little bit trippy if you think about it, but that's what cosmology is studying, is that everything is defined by all the stuff compacted into that point, expanding over time. So the beginning of the universe as we know it is the Big Bang. And then things began to expand. We're going to have a separate introduction to the Big Bang in another lecture, and then another separate one about inflation. That's this extremely rapid expansion. Here we're just going to focus on the more mundane expansion afterwards and talk briefly about the accelerating expansion that is now happening. So when we say expanding, we mean that space itself is expanding. Everything is moving away from everything else, right? So it's not like the objects are exploding or they're all like driving away from each other. It's that space itself is physically expanding. So just like my stomach is steadily expanding over the years, the universe is steadily expanding, right? It's not like it's exploding or anything like that. So a great analogy, it's hard to do better than this, is chocolate chips in a muffin, or in this case, in this picture, raisins in a loaf of bread. I'm going to call them chips. So that, when you bake a muffin and you have chocolate chips embedded in there, they're located in some arbitrary distribution, and as the muffin gets larger, all of the chips move away from every other chip, right? The whole volume expands. And interestingly, when you think about the consequences of this, if you were sitting on one chip and you were observing the positions and the velocities of the other chips, you can think about how it would be different when a chip's closer to you versus one that's further away from you. And you can see that the chips that are further away are moving away from you at a faster rate than the chips that are closer to you. So let's just take a concrete example. Let's take this picture here. So suppose you're this central chip here, and you're looking at the one that's 3 centimeters away and the one that's 20 centimeters away, so the closest and the furthest. Okay, so when at time 0 before baking, your distances are 3 centimeters and 20 centimeters. Then your loaf or muffin here bakes for some amount of time, and after that time, the closest chip is now 6 centimeters away, and the furthest is now 40 centimeters away. So all the distances here have doubled, right? So this thing has doubled in size. But this chip here, the closest one, it went from 3 to 6 centimeters in some short amount of time. The one that's further away, it went from 20 to 40 centimeters in the same amount of time, right? So it covered twice, or not twice, it covered much more distance in the same amount of time. So if this took an hour to bake, then the closer chip would be moving at 3 centimeters per hour, whereas the further chip is moving at an average speed of 20 centimeters per hour. Okay, so then the same thing is going to be true for our universe. The galaxies and galaxy clusters that are closer to us are receding at some velocity. The ones that are much further away are receding from us at an even higher velocity. Okay, so just like chips in the muffin. So this recession velocity, the velocity at which objects are moving away from us, it's related to the distance. So just this is what we qualitatively said here. Now there's an equation. The velocity is equal to this constant, h, times the distance. And so this constant is called the Hubble constant, and it is equal to 20 kilometers per second per megalight year. So that means an object that is 1 megalight year away is moving away from us at 20 kilometers per second. An object that is 2 megalight years away is moving away from us at 40 kilometers per second. So for every megalight year of distance, so that's a million light years, every million light years of distance, you get an extra 20 kilometers per second recession velocity. Okay, now there are also little local, we call them peculiar velocities that objects have, so they might just be moving, left or right or something like that. But this recession velocity we're talking about is its main bulk motion away from us. And it's much more meaningful when you think about very distant objects, right? So galaxy clusters and things like that. It's not really meaningful to think about it when you're talking about the planets in our solar system. So this is a large scale consideration. So let's take an example here. Let's look at the Virgo cluster. This is a nearby cluster of galaxies, relatively speaking. It is 54 megalight years away from us. And so if we want to know what the average recession velocity is of an object within the Virgo cluster, we can take this equation. The velocity is equal to the Hubble constant times the distance. And we see that it's receding from us at around 1,000 kilometers per second. That's how far away it is going. And so everything is moving further away from everything else all the time. Now it turns out that rate of expansion is actually changing over time. Okay, and it gets a little bit complicated to describe it in a precise way mathematically. You can do that in an upper level astronomy course. For the introductory astronomy, let's just talk about it in qualitative terms. Okay, so at the beginning of the universe, we have the Big Bang. We'll talk about that in a future lecture. There's inflation, a very rapid expansion. We'll talk about that in a future lecture. And then we have this expansion that's something more like what we were talking about, this Hubble expansion. But the force of gravity, right, means that everything with a mass is attracted to everything else with a mass. Okay, so you, for instance, are attracted to the Earth. That gravity is what's keeping you down. The Earth is attracted to the Sun. That's what's keeping the Earth in orbit around the Sun. You're technically also attracted to your computer, right? It has mass and you have mass. The force is just very weak in that case. So every other galaxy is attracted to each other galaxy, right? Every single galaxy is attracted to all the other ones. So there's this gravitational pull pulling things closer together. So eventually you'd think that this expansion would basically run out of steam. So it is the case that early in the universe the expansion began and it was actually slowing. And that was true until maybe a few billion years ago, where the expansion was slowing because matter, so objects with mass, was causing this expansion to slow just due to gravitational attraction. And you might think that eventually then the expansion would slow and everything would collapse back in on itself and you'd have a big crunch. We now know, as of the past 20 years or so, that instead acceleration has taken over. And so instead of the universe coasting at a constant expansion or slowing expansion and then contracting, we actually observe that the universe is accelerating apart. So things are moving away from each other at a faster rate over time. And so that Hubble constant that we're talking about in the previous slide, that's the Hubble constant at our current time. That will actually increase effectively, and things will begin expanding at an even faster and faster rate as time goes on. So this is an accelerating universe. And you might wonder, what? How is that happening? Why is that happening? And that's because we need to think about what the universe is made of. It's mostly made of stuff that we can't see and we know almost nothing about. So if we look at the energy matter content of the universe, then around 5% of the universe is, visible atomic matter that we're used to. So the stuff that you're made of, the stuff that the ground and air is made of, the stuff that you can see. Everything you're used to interacting with in everyday life is atomic matter. Then a big chunk, about a quarter of the energy matter content of the universe is dark matter. So this is matter in that it has a mass, it can interact with the gravitational force, and that helped in the first several billion years of the universe slow expansion, all this extra mass. But the reason that there's an acceleration is that the universe is actually mostly made of something called dark energy. And what we know about dark energy is mostly the name. It's some energy content that must exist in order to explain this rapidly accelerating expansion. We don't really know anything else about it at all, which is kind of remarkable. If you think about it, 70% of the universe we know essentially nothing about. 25% of the universe we know very little about. We mostly know what it's not. And then 5% we actually understand to some extent. So that's fun. So the dark matter has mass, doesn't interact with light. That can cause the expansion to slow, but the reason the expansion is accelerating is dark energy. It's responsible for some repulsive force that that evidently is there based on our observations. So how do we know that the universe is expanding? That seems like a weird thing to say, that we know things are moving far away from us at some speed and then it's getting faster as time goes on. So how do we know that? And we need to be able to measure the velocity and the distance, right? That's how that Hubble constant tells you what the velocity is for a given distance. So the velocity, the way we do that, we've actually already covered back in the Introduction to Redshift lecture. So you'll recall that we can look for atomic lines of a known wavelength, and that wavelength is shifted based on the velocity. And if it's moving away from us, that's known as a redshift. Now, one thing to note is this redshift is actually due to space stretching things apart. So don't think so much of cars driving away from each other. Think more of like the chocolate chips in a muffin, right? Space itself is expanding. And how do we get the distance? For that, we need a standard candle. So what a standard candle is in astronomy, it's an object that we believe we know the intrinsic luminosity, how bright it is, and then we can measure how many photons we detect from that object, and the fewer we detect, the further away it is. So recall from the Introduction to Light lecture that light intensity for an observer decreases with the inverse square law. And so if we're very close to a light source, our detector will receive many photons. If we're very far from a light source, our detector will receive fewer photons for the same source. And so if you know how many photons your source is producing, you can figure out how far away it is by how many you collect in your photon detector. And so there are a handful of objects in astronomy which we believe we know the intrinsic luminosity of, and so we can observe them and see what their distance is. One really incredible example is this thing called a Type 1a supernova. It is an exploding white dwarf, or perhaps two exploding white dwarfs. It's a bit of an open question. These things explode and they are extremely bright. And the nature of the explosion is such that we believe we know how much light these things are outputting. And the fact that they're bright is great because it means we can see them from very far away. So what do I mean by bright? This is a galaxy that was observed with the Hubble telescope, and that's the center of the galaxy, its nucleus, and you see many of the stars here, and the reason it's dark is because there's dust and gas obscuring other stars. This object here is actually on the edge of that galaxy, and you can see it is essentially competing in brightness, right? So the light of an entire galaxy is what this Type 1a supernova can output for a handful of days. And so these are objects that we use then to figure out how far away something is. If we can get also a redshift on something in this galaxy or nearby, then we can also, so if we can collect a spectrum and measure the redshift, then we can also get the velocity. And then we know, oh, okay, something that's that far away is moving away from us at that particular velocity. And that is what is done to determine that the universe is expanding. So you might wonder then what's going to happen to everything, right? If everything's just expanding further and further apart, well, stars are going to go their course in stellar evolution. Um, Eventually, star formation will cease. Some of the last objects you'll have around are these stars called white dwarf stars that we'll talk about in a bit. These, in future lectures, I mean, these are very dense objects, roughly the size of a planet, but the mass of the sun. And they're basically just, you can think of them as giant diamonds that are cooling off. It's a carbon-oxygen mixture, so it's basically a big old diamond. And they just cool as time goes on. Recently, it was shown that likely these things will explode in the very distant future. So 10 to the 1100 years. That's a long time from now. And that's one of the last things that's going to happen in the universe is you're going to have some of these white dwarf stars explode. Then, things are moving further apart. They're cooling. These explosions are happening. There's no more nuclear chemical reactions going on. Basically, everything's just kind of moving further apart and cooling, and eventually you have heat death. And heat death means that there's just not energy for anything else to happen. You're in what's called the highest entropy state, the maximum entropy state. So that's it. And then there's essentially kind of everything's nothing again, right? It's all just nothing's going on, which is kind of cool. And on that happy note, that is it for this introduction to cosmology for Astronomy 1000.